Hello everyone. Let's just wait for others to join in and then we can start.
Hello.
Hi Rohi. Sorry, I was on mute. So maybe we can give it a start. Let others join in as well, right? So until the last class, I hope I was able to address at least some of or some areas of the problems or the questions which you had. As of now, where we ended in the last session is that we understood what is the definition of overfitting and underfitting. We understood what is the importance of breaking the data into training and testing sets. We also understood how to get the intercepts and the coefficients. We understood how to list them here, and we could clearly see there are some coefficients which are very, very close to zero. That's what we are going to talk about now. And that we can get rid of. And then we can look at the rest of the coefficients which are actually making some sense and try to build the model. So that's one way of improving the model as well. And let's say finally, we were talking about the R square score. So R square score is the score that explains the variability in the data. The closer it is to one, the better the model is. Now, I'll just write what we have found until now and then we can proceed. So as of now, the model which we have has a good score. Okay, so not very good, but not even bad, right? But it can be improved, right? Which we would do further now. So the first thing that I always do, right, irrespective of whether I have outliers of data or not, or I really need to uh, be bothered about the scale of the data or not. There is one thing that I always do, right, and that is as simple as I take the data and I look at it. Let's say I'm just going to look at it with an info the info function. I believe this is the data set. Yeah, so I'm just going to look at it from an information point of view. Let me just quickly go back and see from where or how I did the X train and Y train. I believe I did it correctly from Boston Final. Sorry, we should be looking at Boston Final, right? So Boston Final is no Boston Final is not from where I did the training and testing. Give me 1 minute. I did it from XY, and X and Y has come from Boston, if I'm not wrong. Yeah. So I did it from Boston data set only. Boston final, I will look at it at a later stage. So Boston is the data frame which contains all the data. So I got the information about all the fields, and I could clearly see all of the fields are numeric. The first thing I would do, if there are, let's say, categorical fields, I'm going to convert it. And I'm going to convert it basis two techniques. We have already talked about the techniques, but I'll briefly go through them once. When to use one. right? So the first technique is to do a one hot encoding. One hot encoding. And one hot encoding is as simple as, okay, give me 1 minute. Yeah. So one hot encoding is as simple as, let's say I have a categorical column which is red and blue. So it has two values, red and blue. If I want to encode this textual data into numeric data, one hot encoding is something like this. Rather than having one column which is the color, let's say this is the color column. So rather than having one column, I'm going to convert this one column into two columns, R and B, or C underscore R, which we will see. This is what sklearn is going to do. Although in this case, we won't be finding it because we don't have any categorical column. So we just have to, let's say, use our imagination here. Later on, we can take other data sets as well, which is kind of linear regression or regression use cases where we have the categorical columns. There it will be practically clear, but as of now you can try to visualize. You have broken down the C column into two parts. One is C underscore R, the other is C underscore B. And if for any row, let's say for row number 1 the value of column C was red, then I put a 1 in this column and a 0 in this column. Then again for row number 5, if the value in the C column was blue, then I put a 1 in this blue column, and 1 and a 0 in the red column, and so on. So this is known as one hot encoding. Now the advantage of this one hot encoding is that it keeps the data within the range of 0 to 1 per column, right? So in any column you will find the data to be in the range of 0 to 1. This is very good because now you have also taken care of the distribution of the data. So it will never have an outlier because you have created the data in such a way. The other way of encoding, I hope you got the point. So the other way of encoding is known as label encoding. So if let's say I have again that same field color, and I can have two values, let's say red and I can have blue. So rather than converting this column C into two columns C underscore R and C underscore B, I keep the column as it is, and I simply replace the values of red and blue with some number. So let's say I will replace R with 0 and I will replace B with 1. So for row number 1, if the value of C in the data set was red, I'll replace R with 0. If for row number 10 the value is blue, I'll replace that with 1. Now this is also not bad. I mean, it is technically doing the same thing as we saw in one hot encoding. But the difference comes when you have more than two categories. In case of more than two categories, so let's say you have R, G, and B, right? So R, G, and B, these three fields are there in the color column. So you can give numbers as 0, 1, and 2. In case of label encoding, you can give numbers as 0, 1, and 2, or you can choose your own labels like 1, 2, and 3. Now, in this case, what will happen is this column ultimately you can visualize it will be in the range, or I can write it something like this. It will be in the range, okay, of real numbers. Of course, it will be in the range of real numbers, but that real numbers will be in the set of 0, 1, and 2. And now it's no longer, okay, it's no longer a normal distribution because your data does not fall within the range of 0 to 1. Right? Your data does not fall within the range of 0 to 1. That's why it can't be termed as a very normal or normally distributed kind of a thing, right? Or a column. So keeping this in mind, the clear-cut strategy is if I have a column which has two categorical variables, and if I have a regression use case, okay, it is a common practice that I use one hot encoding. Okay, and that is exactly what we could have done over here if we would have had a column like that. But if I have a regression use case and I have a column with more than two, no, sorry, I did a mistake here. So this will not be one hot encoding. I'm sorry, this will be label encoding. So having two values for a column and doing a label encoding always retains the range between 0 to 1. Then if I have three values for column C, 1, 2, and 3, then I can do a one hot encoding, right? I can do a one hot encoding so that I can get 3 new columns. I can delete this column later on, and I, instead of having one color column, I get 3 columns, one for each of the values, and for each of the columns the range is going to be 0 to 1. So ultimately I have normalized my data, right? So that's the objective. Now, in case of a classification problem, this is not so much of a problem. I mean, I have personally not seen any such kind of cases where in any classification algorithm you may have to specifically use a specific type of one hot encoding or label encoding. But yes, there are certain cases which may have to take care of. So when we start with the classification algorithms, where we are going to predict whether tomorrow there is going to be rain or not. So yes, no kind of a problem, or yes, no, maybe kind of a problem. Yeah. Then we will be looking into um, we will be looking into this. Okay. So give me 1 minute. Yeah. So for classification use cases, we will look into it at a different way. When we do the classification algorithms, right? We will try to figure out where, when, what we are going to do, and so on and so forth, right? So as of now, in my use case, I have no null data, and I have everything which is a floating point data, which means they are actually decimal numbers, so real numbers, but I don't have to do any categorical encoding. So that's the first information I got. The second thing I do is that if I have numerical data, okay, I'll exclude the target data. I will not be doing anything with the target data, but I am going to do something with the features data. So independent variables is where I'm going to do something, and that is known as standard scalar. Now, what do you mean by standard scalar? If you remember, we briefly discussed it once. Now we are going to see that into action. So standard scalar is where I use that Z score thing to scale my data. And what I mean by that is I ensure, okay, I ensure that my data is standardized and it falls within a range of 0 to 1. Okay, and that's exactly what we are going to do. So let's see what library we have. So we already have this page where it says that in sklearn, I have a module called pre-processing. There I have standard scalar. And obviously, as you may have already guessed, in sklearn documentation, there is already something to take the reference from. So there is some code that I can take a reference from, right? I am going to take the reference from this code and then I can look into it. So, or maybe we can try to find examples as well. So the reason why I'm showing this to you is because, to be very honest, I don't really remember all the libraries or all the functions and so on, because I don't need to, because these communities, right, unless we are using libraries which are not really that hit in the market, or people are not using it, or organizations are not funding it, they usually have, I mean, for libraries like scikit-learn, where thousands and millions of people are using it. So in that case, what happens is the documentation is usually quite up to date, right? So I don't really need to care about remembering all the functions and the libraries and the features and so on. I can simply go to the documentation. I may even be bookmarking it, and then I'll simply go to the documentation. I'll select my version, and then I'm going to go with it. So one quick way to look at the version is that you can, inside this only, you can write a command called pip search, I believe, sklearn. So let me just see if search command runs or not, or maybe I'm going to was it a search command or something else? Let me just see if this command runs. And I think, yeah, it was a search command only. No, it is not. It is actually searching all the libraries. No, this is not the case. So um, let me Google it. Okay, pip find current version of Python library. At the parent of the pip count, pip list, pip show, pip show. That should be the one. Pip. Oh, sorry. Pip show sklearn. So let's see what it shows us. I hope this is yeah, it is not giving me anything. Is this the right command to do? Yeah, pip pip show. So it should it is not showing me anything. I'm not sure why. Let me see pip or I can do this pip list, right? And this will be a big output because I can see the list of all the packages which are installed, right? So let me just see where is sklearn, 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 sklearn. Where is it, man? Scikit-learn. Okay, so this was the name in which it was. Okay, so 0.21.3. Why I found out this is because if you look at this document is for 0.23.2. So let me change 0.21.3. This is the right thing. You can also download a PDF. Okay, and in here you can try to you see there is a pre-processing module here, and here I find this annotation thing. So it should be here only. Yeah, should be this. Yeah. Pre-processing standard scaler. Yeah, here it is. So I can use this and I can do the scaling of the data. Yeah. So let me just even find an example from somewhere. So let's say sklearn dot pre-processing dot standard scaler, and then I'm going to search Stack Overflow. Okay. So this is one cool way in which I can actually get sample code. So example. So I can just do an example like this, and there here I can get some examples from here. So I can get the example from here. They are doing this fit transform, and they have got it right. So good that they have shown us an example. We can just take this as this mean equal to 0, standard deviation equal to 1. I don't have to specify. They have specified it here that I need a mean of 0, standard deviation of 1. I really do not need that. Okay, I really do not need that. If you want, you can give that. I mean, that's not really a very hard and fast requirement. But if there are some, let's say, processing that we need to do, or there are some algorithms where what we need to do is we have to, let's say, uh, uh, standardize the data as a normal distribution only, or otherwise the algorithm is not going to work. In this case, k-neighbors classifier is it's actually one of the classification algorithms which we'll see. So in this case, this algorithm requires the data to be in the form of a normal distribution with mean 0, standard deviation 1. So that's why the x, s, and xt, so the learning data or the training set and the testing set of the features are actually fit and transform, right? So I can do the same. So let me just delete this because I don't need this. I just wanted to show you this. So what I can do from sklearn.preprocessing import standard scaler, right? I have imported standard scaler. Now what I'm going to do, I have to ideal condition, I should create an object of standard scaler. So sc is equal to standard scaler. Okay, I've created an object, okay, which is a sorry, which is sc. And if I do a type, it's going to show me that it's an object. So what I'm going to do now, okay, is that I'm going to take all the x's and I'm going to convert them. So let me look at the x thing. So x is basically having all the features. So if you look at the shape, it's actually going to tell you it has 13 columns. So it has all the 13 columns, right? So I'm going to take X and I'm going to say X scaled. Okay, X underscore scaled is equal to X, SC dot fit transform, and I'm going to pass the value X, right? So what I am essentially doing is now I have X scaled, which is a new variable where all my features are scaled. Okay, now usually what happens is it has picked up a random way of doing the scaling. If you want, yes, if you want, you can also define with mean is equal to 0, with standard deviation is equal to 1, and that also is going to work, no problem. In this case, all the data will be scaled within that range only, right? But this part is actually specific to an algorithm, so we are not going to do it over here because linear regression does not have any such kind of assumption, right, that my features has to be normally distributed. We have already seen this. So features that not does not need to be normally distributed. Your target must be ideal condition. Matlab, the most ideal condition is your target should be normally distributed, but in our case it's not entirely normally distributed, it's close to it, and that will work. But please remember, what I've done over here is scaling that applies only to the training data. Okay, only to the training data. Now this is going to be a quiz for you. Please try to do some research and come up with an answer. I'm also going to tell you the answer in the next class. Why do we not scale, or why did I only scale the X variable and not the Y variable? Okay, this is a good question. You can try to answer this, try to figure out why is that case. Okay, there's a very intuitive kind of an answer. There is a mathematical answer as well. Okay, there is an intuition based answer or a practical answer, and there is a mathematics based answer as well. You are fine with whatever answers you can try to find. Now what I'm going to do, I'm again going to create X train, X test, Y train, Y test is equal to train test split, and I'm going to say X scaled. Now I'm going to use X scaled, and then I'm going to use Y, and I'm going to use test size is equal to, did I use any test size earlier? I don't think so. Let just check this once, because I just want to keep the similarity. No, I did not use. I just used random state 101. Fine. I'm not going to use in this case as well, because or otherwise it's just going to create more confusion as to what difference my previous model and new model has, right? So why to create a confusion? Now I have X train and Y train. So let's see what their shapes are. The X train has 379 rows. Obviously, it will have 13 columns. X test has 127 rows and 13 columns. Very good. Y train, sorry, extremely sorry. Y train dot shape has 379 rows. Obviously, these are the output or target 379 values for these 379 row 13 column training data, and Y test dot shape is going to tell me 127. So that's just a quick check. Now I'm going to create a new model. So LM2, this is my second linear regression model. So the first one was LM1, LM2 I'm creating a new one. So I'm going to say linear regression, right? So this is an object. This is an object of linear regression. Okay. Now what I'm going to do, you know that LM underscore 2, and I'm going to fit the data X train, Y train, right? Now there is something which is coming up on this laptop. I've actually changed my laptop. I have gone over to another one. So in this laptop, you can see that in my earlier laptop, there was some problem. I don't know why it is not printing on the screen. Maybe it is a problem with the version. I'll have a look. So fit intercept equal to true, n jobs equal to none, normalize equal to false. These are some things which are coming up. These are called hyperparameters of a model. You can simply imagine that you have a box, you have magic box, and you use this to show magic, and you have 4 knobs in the box. Okay, you can tune these knobs to increase the level of magic that you are going to show, right? So consider this box to be our machine learning models, which for me, who is a beginner, it's like a magic. And I have 4 knobs: knob 1, knob 2, knob 3, knob 4. The more I tune these 4 knobs, my machine learning will be even more robust. This is not what we are going to look right now. We are going to look it in the next session. As of now, we are going to try out all the techniques we have already written down, like scaling of features and so on and so forth. Then we'll see how we can improve the model performance. If not, obviously we have to do this, or we will try, let's say, different ways of doing the regression, right? So just a quick overview here. Please don't take it so seriously right now, but yes, it's a very, very important factor of tuning a machine learning model. Each and every machine learning model in the world, okay, has a set of hyperparameters. Numbers are going to change. So let's say in this case, you can see how many are there. 4 are there. In case of some other algorithm, there might be 30. I don't know. So it actually depends how many knobs will be there, but not every knob is really as important as the other one. So just because you have a model which has 30 hyperparameters doesn't necessarily mean, oh, I have to tune all the 30 so that I can get a very good model. No, that's not the case. You can selectively tune only 5 out of them, and that will do as well. Okay, so necessarily you don't have to tune all the 30. Okay, but please don't take it so seriously, or in a different way right now. I know it is a bit over the head right now, but when we do that, when we practically do it, it will be clear. Right now I have my new model, right? What should I do? I have to get the new predictions. Okay, so now what I'm going to do, lm2 dot, oh sorry, lm underscore 2 dot predict, and I'm going to pass the test data, right? And then I'm going to say lm accuracy score. No, sorry, accuracy score was not that. There was a different model for yes, R2 score. Yes, but first of all, let's check this. List the feature and the coefficients. List of the features and the coefficient, lm2. So these are the coefficients now. Has the coefficients changed? Let's pick up 2 of them and check. CRIM is now minus 0.80. What was the case for the previous model? This is why I named them LM1 and LM2. Now I can easily compare them. You see, CRIM is now minus 0.8. Earlier it was minus 0.09. Right? So after I have scaled the data, the importance of this feature has actually increased. Why? Because the weight or the coefficient associated with this variable is now more than what it was earlier. Is that a good indication? Maybe, may not be. We don't know that. We don't know that because we have not looked at the R-square score, right? But we have to look at it. So let's check. Okay, let's check this one. So let's delete this, and I'm going to say R2 score, and I'm going to say Y pred Y test. Sorry, and here I'm going to say end of bracket, and now I get an R2 score of 0.60. Okay, so I have two models. I have two models, model 1 and model 2. Model 1 gives me a score, an R2 score of 71.71. And now I have another model which is close to 0.6. Now, what is the meaning of this? Okay, let's try to understand. If I have an R2 score, which is 0.58, I'm just going to take the first 2 points after the decimal, and I convert this into percentage. So in a percentage format, this becomes, let's say 60% or 58.82%, right? So if it is 60%, this value represents that using this model, okay, LM underscore 2 is my new model. Using LM underscore 2, I was able to get hold of, or I was able to explain, okay, 60% of the variation of the data. The rest 40% is not explained by my model. In other words, my model only explains 60% of the cases, or my model is fit or generalized with only 60% of my data or its variation. It's not fit, or it is not suitable for the rest 40%. Right? So this is the way we can explain the R-square score. So obviously, as I told you earlier as well, if I'm explaining these things to my management, obviously they may or may not be data scientists. They may not even be from a mathematical background. How will they know? How will they come to understand what is the value or what is the meaning of this R square score? So this is how we can explain. Now, what was the earlier model, LM underscore 1? LM underscore 1 was close to 72%. So using the first model or the earlier model, I was able to explain 72% of my data. After I've scaled it, I've actually disturbed it. Now, is that a problem or no? I don't know that. I don't know that. Yet, I'm not going to say that I know that because of scaling only this has happened. Okay. Give him 1 minute. In the meanwhile, maybe if you have any questions.
No questions.
Okay, fine. So now I'm again not going to believe that my model or my activity is really bad. I'm going to push myself to a very good limit now. So what I'm going to do now is that I'm going to take this Boston final. I'm going to take Boston final and I'm going to create my X and Y and I'm going to scale them. Okay. So I'm going to say we are still not satisfied with the model, or even we cannot really say that the first model was better than the second one, since in the first model, even if even if I have a higher R2 score, I in both in none of the models have considered the most important variables or features which we found as part of RFE and VIF, right? We have not considered that. So what I'm going to do, this English has a bit of a problem. Let me just quickly correct this. I have not considered, right? So I in none of the models, oh sorry, have considered the important factor. So what I'm going to do now, I'm going to use Boston final. So Boston final is something like this. And here, let me see Boston final, Boston underscore final dot columns, and I get the list of the columns. So what I'm going to do, I'm going to create an X. This is going to have these columns, and I'm going to create a Y, which is going to have, no, sorry, I made a mistake. Let me just correct this. No, sorry, again a mistake I have done. This will be double brackets actually. So let me go over here. Yeah. And here I'm going to say Boston underscore final. I'm going to say MEDV. So this is my X and Y. Now I'm still a very big fan of scaling the data. Okay. I'm still a very big fan of scaling the data. So let's scale the data again. X scaled is equal to SC dot fit transform X. Right. I have taken X and I have scaled it. So this is my X. X is a data frame and X scaled is now an array which is scaled, right? Now what I'm going to do, I'm going to take this data and then I'm going to do the X train, Y train, X test, Y train, Y test is equal to train test split X scaled and Y, and I'm going to say random state 101. So I have my training data, which should be of the same size. I'm just trying to check if it is not. And then I have my Y train, which should be of the same size as well. Now, X test dot shape and Y test dot shape also I'll check quickly. And it is all fine. Now I have only 5 columns. Okay, I have only 5 feature columns. Now let me create my new model, which is LM underscore 3. LM underscore 3 is equal to linear regression. and then I'm going to say lm underscore 3 dot fit with the training data x train, y train, right? Now I'm going to say lm, no, I'm going to first of all go back and do a copy paste. I'm going to do this copy. I'm going to come over here. I'm going to put it over here, and I'm going to say this. Now, as you can see, somehow my model, I don't know whether it is really good or not, but if you look at the values, okay, the values are not close to zero or very less than zero or very high and so on and so forth. So variation is not there. Now, why I am repetitively talking about these coefficients here, right? I can also look at the intercept. lm-3 dot intercept should be something like this. So the intercept has also dropped. Now, why I'm saying this, let me quickly share that with you. Then you should be able to understand what is going on over here. So if you remember the formula of multiple linear regression, I'm simply going to write it over here. Okay. So I have theta 1. I'm going to write the thetas as t. Okay. So t0 means theta 0, right? T0 or t0, which is my intercept, right? And then the coefficient t1 x1 plus t2 x2 plus t3 x3 plus t4 x4 until tn xn. So I'm just going to take only 5 plus t5 x5, right? Now why did I take 5 is only because here I have 5 columns. Now each and every weight are these thetas. Okay, so these coefficients 1.017, let's say, is t1, minus 3.37 is t2, 4.6 is t3, minus 1.9 is t4, and minus 2.74 is t5. These are, you can also call, the weightage of these variables, which means that x1 has a weightage of positive 1.01, x2 has a weightage of minus 3.4, and so on. Now, if a weightage, let's say I had another variable, let's say, just for a minute, I'll assume I had another weight t6 attached to another feature x6, right? I had another feature x6 which had the coefficient t6, and this coefficient is, let's say, the value of this coefficient is 0.0031. Is that really a very important coefficient? The answer is no. The answer is no. Why? Because these coefficients are found out by means of that same gradient descent exercise where we have done a descent towards the global minima, and my model has tried to find the optimal values, right? The optimal values of my thetas or my t's, the set of t's for which the error is 0. And one value out of that set is t6, and that value is very, very small. So the effect of x6, I can say, on the target variable y is close to 0. It is negligible because this value is very, very lesser than 0. Hence, there is no point of using x6 in my model. And now if I reverse engineer this concept of mine, I can clearly see that in earlier models, I had some places at least where I had very huge or very small data, which is an indication of something being wrong. If you look at the same output, if you look at the same output, I'll just copy it over here and I'm going to say B, and here I'm going to just put it over here. Yes. So just a quick note, the way I added this new cell, right, is by pressing escape. So this cell turns blue, and then you can press B. So if you press B, you enter a new cell. The more times you press B, as many cells you want, you can press B, right? And if you want to delete this cell, you can simply press escape and press DD, right? So the cell is gone. Now I'm going to compare LM2 coefficients with LM3 coefficients. You can clearly see there were many coefficients which were closer to 0. So there, the model was not doing a correct job, or model was not able to find the right set of things, right? So that's exactly what we have found. We still don't know. We still don't know if my model LM3 is good or not. I don't know that. You can never know. You have to test this kind of different models, not only on in paper kind of a scenario that we're doing right now, also in the practical use cases or practical, let's say, scenarios using things like A/B testing and so on. And then only, right? And then only you come to a situation where you will come to know which model is actually good or which features are actually contributing more and so on. right? Now, but let's just look into the R2 score. But to look at the R2 score, I need the prediction. So let's do the prediction. LM underscore 3 predict and X test, right? R2 underscore score is Y pred Y test. And the score is even lower. The R2 score is even lower, even low. It means clearly my selection of columns is not good. My selection of columns is really not good because this selection of column has actually reduced the R square score. If the R square score is reducing like this, then my model is really not good. This is an indication. Only looking at the coefficient, it is not going to help. I also have to look at this. Now, there is one more thing which we have to look into as well. Because we have three models, we can look into them right now. sklearn, RMSE, root mean squared error. Root mean squared error is a very, very important metric. We are going to apply it first and then we are going to look at it. So what I'm going to say, from sklearn.metrics, import mean squared error, right? And then I'm going to use this function just like this, mean squared error. Just like this, I'm going to use this function. I'm going to use this function and I'm going to say y test and y pred. It gives me some value. Now I don't know what this value means, right? Now I have made a mistake which I have to correct. Okay, I'm going to call this a mistake, right? I'm going to call this a mistake because I should have given proper variable names to each and every case. Hence, I'm going to go back. I don't want to run the entire notebook once more. So I'm going to go back. I'm going to go back again here. Okay, here I'm going to come over here and I'm going to say X test, Y test. Where have I taken X test and Y test? I think I have taken it over here. Yeah, X test, Y test, and I'm going to say here. So I'm just going to add a new cell and I'm going to do this Y test, Y pred, right? Then I'm going to again enter a value. Give me 2 minutes, you will come to know what I'm trying to do. Again, I'm going to come over here, enter a new cell, and I'm going to do this. And then I'm not going to run it. I'm not actually executing it. You see what I'm trying to do over here? I'm not executing it. I'll go back. Okay, I'll go back and I'll start running from the original test trend split. Okay, now I have the first model where I have X train, Y train, and I have all these values, and I have the features, I have the intercept, I have the R2 score. It has actually decreased. I don't know why. Let me just see if I've taken all the features or not. No. Have I taken all the features X and Y? No. I think I have to go back. I have to go back and I have to take it from the place I have taken X and Y. So where is X and Y? Let me just go back. This is just going to be a 1 minute job, so no problem. So I don't think I was at this place when I took X and Y. X and Y should be here. So give me 1 minute. I'm just trying to find where I have taken X and Y. I think this is the place. So feature columns, Boston final. No, where is X and Y, man? Let me just see where is X and Y. Okay, so I have taken X and Y on top only. Fine. So I will just quickly run all the cells. But what I will do is this using sns.scatterplot, right? I'm just going to hide this. Okay. I'm just going to hide this so that we save some time. Okay. I'm just going to hide the graph so that we save some time. I'm just going to hide these cells. And now it should give a very good and quick outcome, right? So this is one of the advantages of using Jupyter Notebook is because you can go back and you can change things. And then you can rerun the entire analysis as you fit or as you see fit. So then what I'm going to do, I'm going to come down and then I'm going to say until here. Okay, until here. No, this is RFE. Let's not look at RFE. This is here. Yes, until the model. until the model. We have to start from here again. So I'll say, I'll go to cell, I'll save this first. I'll go to cell and I'm going to say run all above. So I'll just wait for 2 minutes for everything above that cell to be executed once more, right? And that's going to give me a fresh set of data where X and Y will be the original fields. And then I'm going to start again. Okay, so let me start again. I think now I have all the fields. You see 13 fields are there. I've taken X train, Y train, and I'm going to do a small change over here. I'm going to change this to _1. Okay, so I'm no longer going to use X train, Y train, this kind of names. I'm going to use names like these. Okay, I'm going to use names like this, so that it is easy for understanding the model, right? So first of all, let me see. Yeah, this goes on, this goes on. Very good. Prediction is there. I have the data frame and I have the scatter plot. The scatter plot is not very bad. It's quite good. And then I have the coefficients, I have the intercept. Okay, now I have the R2 score, and then I'm going to find the accuracy. As expected, we are back to 71%. First model had 71%. And my mean squared error is 30. Okay, let's note this down. Let's note this down because we don't want to do a to and fro again. So LM1, okay, mean squared error or root mean squared error, sorry, root mean squared error is 30 point something. I'm going to just say 30. So root mean squared error is 30, and my R2 score is 71%. Okay, so R2 is 71, right? Then I have another model, then I have another model, right? I'm just going to see what is the values. Okay, what is the values there, right? And then I'm going to put it over here. Now again X and Y. Again my X and Y. Now I'm going to say _2. So this is one technique that you can also use. In this way, you will have track. Okay. So now I'm going to say this, this, this. I'm intentionally not executing them because I know. So there is no point of running them again. So now what I'm going to do, vibrate 2 using XTest 2. And now I want a coefficient cell. It has come down. Why has it come down? Why does it have only 5 fields? Let me just see where I have made a mistake. Standard scalar. Okay, this is where I ended. Boston.info x.shape. X.shape and x scaled is there, and I have 13. So x and y, x train true, test 2. Okay, LM2. LM2 I have created x train 2, y train 2, and y pred 2. Then now, yeah, I don't know why it did not work earlier, but it worked now. Good. Now _2. So I'm going to do an _2. I got an R square score of 0.58, obviously, as expected, and I got a mean squared error of 30. So mean squared error is 30, and R square is 58. Okay, I'm just going to take. Sorry. Okay. So let me just save this as well. And then I have this data here. I have X and okay, now I have a different X. So I'm just going to say small. Okay. Now Y remains the same, so there is no problem. So I'm going to rename this as X small. So X small is not there. So let me just run this. So now I have X small, which has a small set of the data, and then I have X scaled. And here I'm going to say part 3, 3, 3, 3, X scaled is fine, Y is fine. I'm going to take this, and then I'm going to say 3. I'm going to say 3. I'm going to say 3. And I'm going to say 3. So now I have LM3, and inside here also I'm going to put the underscore 3. Now the model is there, and I'm going to look at the coefficients. The coefficients may not have changed much, but let me look at the intercept. Intercept is also almost the same. I have not much change. So let me just look at prediction and testing. Why pred 3 is not defined, sorry. Now I have got an R2 score of 0.36, 0.36. So this is 36. And what is the mean square value? It is 39, it is 40. So it is 39, right? Now why I did all this exercise and why did I write down? Any term that says error, obviously I have to reduce the error. My ultimate goal whenever you are doing machine learning, you have only two goals. Don't look at accuracy, don't look at the prediction, don't look at any confusion matrix which we are going to look at very soon in case of, let's say, classification use cases. Look at two things first. Always try to optimize the process and reduce the error. This is your prima facie objective. If you have not done this, you forget looking at the prediction, right? But what is happening over here is, as I move from LM1 to LM2 to LM3, my RMSE is actually increasing. Until LM2 it was all fine. Look at what happened to LM3 when I selected those five columns, right? I have done a blunder now. Now I have an RMSC which is even higher, even R2 score is lesser. This model is definitely not good. I'm going to say model is clearly not, sorry, clearly not good. Okay, this is really not good. These two models, this is, I can say, overall good. This is not very good, but not worse as well, right? But look at the third one, model performances. Okay, look at the third one. Third one is very, very bad. You can actually put this into a data frame as well if you want. You can actually put this into a data frame and you should be able to look at it or visualize it as well. So LM1, LM2, LM3, it did not work. LM3 did not work at all. Now I don't know whether this is because of scaling or non-scaling, because when I didn't scale the data, I got a good RMSE and good R square, right? So clearly it is going to depend on what you are trying to do. Again, let me go back. We have some time, right? Let me go back. Let's utilize the rest of the time, okay, that we have today as of now, okay, to do this. So I have X. X has been scaled, okay. And what is the shape of X? It has the 13 columns. So I'm not now going to take X. No, I'm going to take Boston dot info columns. So maybe I'm going to do something over here. What did I do, man? Okay. I'm going to convert this to code and I have to run this. Fine. So now what I'm going to do, what I wanted to do is this. I'm going to convert this into a text. I'm going to write this so that it's easy for me to find it out later on. Not sure why it took it like that. Model performances. So right. So now what I'm going to do, I have these columns and I'm going to create a new X, which is Boston. Okay. And I'm going to take the entire list. I'm going to put it over here and I'm going to remove MEDV. I'm again having an X and Y is going to be Boston MEDV. I'm kind of a bias, or this bias variance trade-off is not really solved within my heart. So I'm still a very big fan of, let's say, scaling the data. So let me again create X and Y. And now I'm going to create X scaled is equal to SC. Okay. But now I'm going to create a new SC. SC2 is equal to standard scalar. And I'm going to say width mean is equal to 0 and width standard deviation is equal to 1, right? And then I'm going to say X scaled is equal to SC underscore 2 dot fit transform, and I'm going to say X now. Okay, so I've got X scaled. Now I'm going to say X train for X test for Y train for Y test for is equal to train test split, and I'm going to take X scaled Y and random state 101. I always forget this. I don't know why. Right now I have done this. So X train underscore 4 dot shape, X test underscore 4 dot shape, Y train underscore 4 dot shape, and Y test underscore 4 dot shape. It looks fine, right? It looks fine. So I have all the 13 fields. Now I am doing a standard scaling. I'm not removing any fields. I'm again doing a standard scaling, but in a different way. Okay, so let's see if that helps. Okay, let's see if that is going to help, right? Now what I'm going to do, LM4, okay, linear regression, enter. LM underscore 4 dot fit. I'm now going to use X train 4 and Y train 4, enter. Now I'm going to say Y pred 4 is equal to LM underscore 4 dot predict, okay, X test 4, right? Now I need the list and the coefficients. So let me again do that for LM4. LM4. So here I have the coefficients. They are almost same, if I'm not wrong, for the first model. I'm not sure. Let's not compare that right now. We are going to look at R square values and so on. So R2 score is equal to Y pred 4 as compared to Y test 4. R square score is 0.60. Okay, so I come over here and I write this LM4, LM1, 2, 3, and this one is 4. RMSE, I have not found it yet. I'm going to write it. R square, can I say 59? Yes, I can say 59. And then I can say mean squared error, Y pred 4, Y test 4. And I get a mean squared error of 30. I get a mean squared error of 30. Right? Did I do anything wrong? No, I did not do anything wrong. I've just changed the scaling as well. So I have 4 models, and this is where no scaling I have done. Okay, this is where I have done out of box scaling. So I have not used any parameter. This is where I have done scaling plus reduced features. And this is where I have done, okay, normal distribution scaling, right? So these are my models, okay? Finally are as follows. Okay, so I can just take this and I can put it over here and I can say this. Okay, so clearly I have 4 models and I see this kind of a variation. If you ask me, I will select the first model out of this. Right, overall it gives a very good shape and structure, right? And it also has lesser RMSE as compared to these 4. So what you do if you have 4 models or 5 models like this, Please don't be not scared. We are going to create more models. Okay, we have just created 4 models right now. These are only linear models. I have not even told you that regression can be done using non-linear models as well. So tomorrow again we will do a lot of other modeling as well. Again, we have to continue doing this. This is a very reproducible kind of a process. If you want, you can start creating functions to do this as well. In many cases, I write functions to let's say do all these things. So I'll write all this code inside a function. I simply pass the variables and run that function, which makes my research very repetitive. But this is what it is. This is the life cycle, my friend. You have to do this. Please don't create one model and come to a conclusion. Create 10 models, 15 models, and then you pick the best out of that model. Actually, this is a technique, and that technique is something which we are going to learn when we look into finalization of the parameters. At later stage, we will look at this technique also. This is also known as this is actually a machine learning algorithm which uses this fundamental, otherwise known as a random forest. So we are going to look at that at later stage. But ideal condition, try all the kinds and types of models for multiple different times with scaling, without scaling, out of box scaling, normal distribution scaling, with less columns, more columns, and so on and so forth. And then you come to a conclusion. You can't conclude only by, okay, I have fit my data, I've got my model. No, please don't do that. Because obviously we knew that scaling the data is going to remove the outliers. But in this case, the places where we have scaled are the worst, right? The places where we have scaled are not really good as compared to the place where we have not scaled the data. The places where we have scaled, they're actually performing lesser than the places where we have scaled the data, right? So this is where the thing is. So we are trying a lot of things, right? I'm trying a lot of things, and then I come to a conclusion, right? I hope until this point in time it was clear. Let's call it a day for today. I'm going to share the notebook and the video as well, obviously. If you have any questions, Rohit, please do let me know. Yeah.
Okay, okay.
Okay.
Thank you.
Thank you, Rohit.